Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this video, we will learn three things: the input shape of a tensor into the convolution layer in PyTorch, the input shape into the fully connected linear layer, and thirdly and most importantly, the conversion of your tensor that you have to do while moving from the last convolution layer to the first fully connected linear layer. And I would say this third point, that is the transfer from the last convolution to the first linear layer, is where the most confusion comes for beginners in neural network. So let's jump in. And first, I'm looking at the official documentation of linear layer in PyTorch. And so it says the torch.nn.linear, it takes in features and out features. This is where you have to define the two variables here. In features, size of each input sample, and out feature, size of each output sample. Now let's look at conf2d documentation of PyTorch. So here torch.nn.conf2d, and it takes in channels and out channels as the first two arguments. And in channels here means the number of channels in your input image, and out channels is a number of channels which will be there after the convolution is applied, that is at the output end of this particular layer. And important thing to remember here is that these in channels or out channels for the conf2d is completely different thing compared to the in features and out features of a linear layer. Let's quickly do a quick example for the linear layer. So here I'm creating a fully connected layer using nn.linear. I'm passing in features to be a number 4 and out features to be number 3, bias false. Meaning I am defining a linear layer that accepts 4 input features and converts them into 3 output features. And for this conversion, we know that weight matrix is needed to perform this operation. But where is the weight matrix? Where am I defining it? The answer is PyTorch linear layer class uses the number 4 and 3 passed in the constructor to create a 3x4 weight matrix. Let's quickly check that that's exactly what is happening in the source code. So I am just going to this GitHub PyTorch source repository, and I'm looking at linear.py line number 79. That's where my linear layer init function, that is a constructor, is defined. And if you quickly check, this is my linear.py, and this is the class linear, and then within it first comes this underscore init method, and that's where these weight creation calculation will be done. And as we can see that self in features, out features, and then there is a self.weight. This line is where the weight is created, and self.weight equal to parameter torch.empty, then out features, in features, and also it takes a variable number of kwargs argument. So that's how in this line inside the constructor of this linear layer, the weight matrix will be created to do my conversion from these in features to out features. And now, before deciding on the shape of in features or in channels of the tensor that will be fed into these layers, let's quickly revisit 5 different shapes of tensor that we will be dealing with in our conf2d and linear layer. So here is an example: torch.size, for example, 16. This is a scalar. That means it's a one-dimensional tensor. This 16 probably is denoting only the batch size. This is used mostly for target labels, vectors, or target predictions. Then I have a two-dimensional tensor, torch.size, for example, 16 to 56. Here they represent batch size, number of features, and this is the form that is used for the first layer in nn.linear, that is my linear layer. And then I have a three-dimensional tensor. Here 10, 1, and 2048, I have taken these numbers as an example, and here 10 represent batch size, then I have channels, and then number of features. And this normally is used in conf1d and sometime also in recurrent neural network. And then I have the very well known and most popular 4-dimensional tensor, 16, 3, 20, 8, 28. These numbers are taken as an example. Here 16, the first one represent batch size, then channels, then height and width. And remember, this is the way PyTorch determines the shapes to be fed into a conv2D layer. So in PyTorch, the first dimension is batch size, then channel, then height and width. This is the most important thing to remember, because accordingly you have to reshape or resize your tensor for various layer. And this structure is specifically for PyTorch. In TensorFlow, it is slightly different. And I also have an example of 5D tensor. This is rarely used because here I have an extra dimension depth, and that's used for conv3D. But in our examples for this video, we will be dealing with mostly this 4-dimensional tensor and the 2-dimensional tensor. Now let's feed an image to nn.linear layer. Let's say I have an image of shape 28 by 28 here, and that is represented in an image vector which is of shape 28 by 28. Now this 28 by 28 pixel image can't be input as 20 as a vector, something like this 28 comma 28. I cannot input this tensor to a nn.linear layer. This is because the nn.linear will read it as 28 batches of 28 feature length vectors. That is, the first dimension will be taken as a number of batches by nn.linear layer, and the next dimension, this will be taken as a number of features, since it expects an input of batch size by number of features. That's how linear layer work. That is, linear layer expects one second, let me take it. Linear layer expects image to be fed into its layer in this format, that is batch size, number of features. So how do I feed my 28 by 28 image to a linear layer? And so to do that, I have to reshape my image vector to this form, that is batch size and number of features. And I can do that with the PyTorch's view method. And this is the kind of code that you have to use, and you will see this classic line of code many times in any neural network architecture, that this image, this vector here, is your original image vector, which can be of any size, 28 by 28, 32 by 32, or whatever, 256 by something else. Then you apply view on that. The first dimension is batch size, because we already talked about the first dimension necessarily need to be batch size for nn.linear. And then you pass a -1, which means that by passing the -1, basically I am telling PyTorch, you figure out this other number, that is the second dimension, for me please. And because the first is fixed, first has to be batch size, whatever the layer it is, how much ever deep your neural network is. For a linear layer, first dimension has to be batch size, and the second dimension I am putting -1 to my view method, means PyTorch will determine it for me. Let's actually see an example to then everything will be cleared. So for this example, I am defining a batch size equal to 1, and I am actually simulating a 28 by 28 pixel image, that is grayscale pixel image, with these vector. That is, input image is a vector which is defined as torch.randn, and I'm passing 1 28 28, that is one channel, 28 height and 28 width. So this input image just will be a vector that will have an image. Let's run this cell to be clear. Yeah, so my torch.size is 128 by 28. So this is my input image, but as we just discussed, I cannot use it directly into my nn.linear. So for that, what I have to do is reshape it by this line of code. That is, I am transferring or converting my input image to this view. That is, first dimension is batch size, which I have already defined to be 1, and the next dimension I'm putting it to be -1. That means PyTorch will decide or infer it for me. This is an inferred dimension, and let's see now what it prints. All right, now I got 1 by 784. That's exactly what I needed for nn.linear layer. So what it did is kept the batch size to be 1, because that's what I have defined at the top. And the next dimension, second dimension, is just 28 multiplied by 28. That gives me 784. And that will be this vector is completely ready to be input into my nn.linear layer. Let's do that now. And with this line, I'm creating a linear layer with 7, 8, 4, and 10 as my in features and out features. Remember the documentation? We saw linear layer take in features and out features as the first and second dimension. That's exactly what I'm doing here. 7, 8, 4, that's my in features. And now I want to this fully connected linear layer, I want to feed my input image, this input image, and we will see that if it builds correctly. So I'm passing in this simulated input image to my fully connected layer by just doing this line of code, fc, and then within braces, input image. This input image is coming from here, which we already saw is of size 1 by 784. And now run this cell, and it ran properly. I got the output size as 1 by 10. 10 here, again, it is out features, which is like, in this case, you can say this is a number of output features after this linear layer. And now I'm going to see an actual example given in the PyTorch official documentation of implementing a full neural network. And this is this page where this is a tutorial page, and they are implementing this particular network. By the looks of it, looks like this is Lenet 5. All right, that is not important. The important is how they are implementing it and how they're calculating the input shape at various stage of the network. So basically this network here, the input is a 32 by 32 shaped input images, and it looks like it's a grayscale image. Then I have a convolution layer where it is converting it to 6 channel and 28 by 28. Then I have a subsampling, then another convolution, another subsampling, finally a fully connected linear layer, and then couple of more layers, and then I have the final output of 10 classes. So what I'm going to understand now, that how they are calculating, how they're implementing this architecture by calculating the input shape at various stages. So let's look at the code that they have used. All right, so this is the code, that class net, this whole class here, that is this whole class will implement this architecture. So let's see. So initially these at the first stage I have a conv2d layer, so they are giving 1, 6, 5. Here 1 is my in channel, 6 is my out channel, and 5 is here stands for a kernel size actually, and because it's a 5 by 5, that is a square metric, so we can actually select a single number. They are very clearly saying it. 1 is input image channel, 6 output channel, 5 by 5 square convolution kernel. Then I have another convolution, 6, 16, and 5, going by the same argument definition. And after these two convolution, I have my linear layer. Now this is the important stage, that this was my final convolution layer, and this is my first linear layer. And let's look how they are defining these shapes here. So the final convolution layer has had these in channels, out channels. For the linear layer, we already know from the documentation, again it takes in features and out features. Now let's understand. They have selected the in features to be 16 multiplied by 5 multiplied by 5, which gives me 400, and then 120 as out features. Now the question is how they decided on this number. Why exactly 400? Let's understand that. Now to understand this number 400 for the first linear layer in here, that is 16 into 5 into 5, I have to understand how a tensor needs to be reshaped while moving from conv2d layer to a linear layer, and there is a rule for that, and the rule is this. First, conv2d will output a 4-dimensional tensor, but nn.linear layer will only accept a 2-dimensional tensor. So I cannot directly feed the output of the conv2d layer to my linear layer. Hence, I have to make a reshaping of the tensor here. So this is the rule. When transitioning from a convolutional layer output to a fully connected linear layer, resize your tensor from 4 dimension to 2 dimension using view method. And of course, instead of the view method here for the reshape, I could use some other method like flatten or even reshape, because the ultimate goal remains the same, that is to reshape my 4-dimensional tensor, which is output of the conv2d layer, to a 2-dimensional tensor to prepare my data for feeding into the linear layer. So in this particular case, for this example in PyTorch tutorial, they have used the flatten method to do the reshape mechanism. Of course, later in a second, I will implement view instead of flatten and check the numbers are working. So basically under these underscore init, which is a constructor, my model is defined, and then these models are invoked one by one within the forward method. So basically in the forward method, you have the input from one model coming from the output from the previous model. So for example, x is output from my conv1, and then this x goes to the input of conv2, and then I do flatten. So after conv2, I get an output x, then I flatten this x, then this x goes to the input from my fully connected layer, and again my the result of this fully connected layer x goes to the next fully connected layer, and so on. So what I have to do to check these, how this 400 is coming, I have to include a print statement in my forward function, and before applying this flatten, let's do that in my VS Code. So my last convolution layer ends here, and only after that I'm applying flatten. So I have to include my print statement over here. So I just included a print statement by printing x.shape, and let's run this cell. All right, I get a 4-dimensional tensor here, 32, 16, 5 by 5. Here 32, just as we discussed in PyTorch, and the first dimension is always the number of samples in a batch. So this is that number. And then I have my channel, and then I have height and width. So batch, channel, height, width. And now I am going to check that this 4-dimensional tensor is being reshaped to a 2-dimensional one before feeding that to my fully connected layer. And so that's the job of this flatten, that this is doing the reshaping. So let's include a print statement here, that will be shape after my flattening. So I just included, I'm just printing this x.shape after the flattening as well, and run this cell again, and indeed my tensor now is a 2-dimensional one, 32, 400, and you see this 400 number. That's how I'm including it here, that is as the input in features for my linear layer, that is 16 multiplied by 5 gives me 400, because after the flattening, after the reshaping, that's the size I'm getting. And 32 here again represent the batch number. Remember, that never changes throughout the layers, between all the layers, how much of a deep that is your neural network architecture, the batch number remains the same. In this case, it was defined to be 32. So now that's how I'm getting my 400 after this reshaping. And this is a kind of pattern you will always see in mostly all neural network architecture with PyTorch, that after the last convolution layer, you will get a 4-dimensional tensor, and then you have to reshape it to a 2-dimensional tensor by use of either flatten or torch.view or torch.reshape. And so just like we thought that I am going to replace this flatten with a view. So exactly the similar job I will do with the view, because in mostly all public GitHub repos and Kaggle, etc., you will see implementation of this torch.view method here. And that the job that they are doing is the same. So here as well, I'm actually flattening or reshaping the tensor. And the first dimension, I am keeping it as batch, because x.shape 0, that represents a batch number. We already saw that x.shape gives me, x.shape gives me this vector, this array or list, and the first element is 32, and that's why I'm keeping x.shape 0 to my view, because I always want to keep the batch as constant. And then -1 just means that I'm telling PyTorch that decide the second dimension for me, and then PyTorch will do the required calculation. And so basically means this second dimension will be inferred based on my input shape, and after considering the first dimension has been fixed at 32. So with this, let's run this cell. And right, I got these working again. So before the reshaping, I had a 4-dimensional tensor, and after the reshaping, I got again the same 2-dimensional tensor of 32 by 400. And all right, and so that's how it is decided. And if you are thinking that okay, so I got these number to be 400, and how come this 120? This 120 is out features, and that is coming from the architecture. So the architecture that this code is implementing is this, like we saw. Yeah, so this is architecture, and by the design of the architecture, after the first fully connected layer, the output of this first fully connected layer is 120, and that's why they have used 120 as a second argument to nn.linear, because this is just coming from the design of the architecture. So now let's just also check the final output from this network. So just comment out this to print line, and so here I am just creating a net object from this my net class, and then I am defining input variable. This is just to simulate an image to be an input image with torch.random, and 32, 1, 32, 32, they're all again batch number, channel, height, and width. It is a black and white image that this architecture is about, and grayscale image. That means that's why I'm passing the channel as 1 for the input image, and the output will just be net, and to the net I'm passing input. And let's just check my output.shape. Yeah, so output is 32 by 10. Here 10 means the final outcome from this architecture again is 10 classes. As we can see, output is 10 target classes, and that's exactly what I'm getting the output as. And 32 here again is a batch number. Let's just see another example, another random neural network architecture example. So this architecture I got from somewhere from the internet, and here again this code is just implementing a neural network, and that neural network is consisting of a conv layer and then another conv layer. Of course, there's a max pool within these two conv layer, and after these two conv layer I have a linear layer, and then lastly a softmax layer. And now let's see again that why. So the first conv layer takes 3 by 16 by 3, and here it's a color image that we are talking about. So the channel number is 3, and so the key point that I want to point out is that my first conv layer ends here, and there my input in channels, out channels are shaped like this, 16, 32, 3, and then my self.linear layer, that is the first linear layer, I'm giving the in features to be 32 multiplied by 7 multiplied by 7, and C remains number of classes which has been defined at the top, C equal to 10. Now why is this? Where from this neural network got this particular number? How come no other number? How come just this? That is, if you multiply this number, you get 1568. 1568. So why the in features is 1568? And again, you can do that by just including, just like we did in the previous example, include a print statement in my forward function, because within the forward function is where I am invoking all these layers. I'm getting the input from one layer, and taking the same input for my next layer, and thereby at each layer, at the end of each layer, I can check the shape of the previous layer. And normally when you are beginning in neural network, and even if you are a seasoned practitioner, it's normally a good practice to check your shape of your architecture by printing the shape at the end of various layers. So I'm going to do this thing here, print shape of x before linear layer, x dot shape. And now if I run this cell, and again this cell, I'm doing exactly the same thing. First I'm defining my entire neural network architecture within this class, and then I'm invoking this class. I'm creating a dummy data here. This is just simulating an input image. 32 is batch number, 3 is number of channels because it's a color image, and 64 by 64 is height by width. And then I am invoking this net, that is the CNN C classifier, with this input image. Let's run this cell. All right, and you can see that shape of x before linear layer printed 32 by 32 by 7 by 7. Here again in PyTorch, the first dimension is always batch number. So my second, these three dimension 32 by 7 by 7, these needs to be combined. This needs to be together before I can pass this tensor to my linear layer, because this is a 4-dimensional tensor, but linear layer I can only pass 2-dimensional tensor, and hence this line here, fc1, that takes this line here. I'm using view to the view, so I got my x here. To that, from that x I am using view to reshape it, and for the first argument to view, I'm passing x dot shape 0, which will give me 32, because batch I cannot change. It has to be, the first dimension has to remain batch always. And for the second dimension, I'm just including -1. That means PyTorch will decide it for itself, and they decided it will be 32 into 7 into 7, which is 1568. And that's exactly why for my designing of the architecture here in the linear layer, I am passing 32 multiplied by 7 multiplied by 7. I should also check the shape of x after here. Let's include a print statement here. Shape of x after the first linear layer. All right, makes sense. Run. Let's zoom out a little bit. Yeah, run this cell again. Yeah, and you can see I got a 2-dimensional tensor. That's what was needed for my linear layer, and that's the same principle that we followed in our previous example here in the official PyTorch tutorial. And this was just another example. And so this is very standard, very typical, very classical pattern you will see in almost all neural network involving PyTorch, because wherever you have a conv layer, and then at the end after the conv layer you want to do a linear layer fully connected once, and then you do this reshape. And to summarize at the end, so this is a rule for transitioning from a convolution layer output to a linear layer output. I must resize the convolution layer output, which is a 4-dimensional tensor, to a 2-dimensional tensor using view method. An example, a conv output of 32, 21, 50 by 50, that is batch number, channel, number of channels, height and width, should be flattened to become 32, then 21 into 50 into 50. That is, this is a 2-dimensional tensor. Remember, don't get confused here. 21 into 50 into 50 is a single number. It's just a second dimension, but here they were separated by commas, so it is a 4-dimensional tensor. So that means for the linear layer, the in features of the linear layer should be set to 21 multiplied by 50 multiplied by 50. Again, this is a single number. And this just denotes the second dimension. The first dimension continues to be the batch number. In this case, it's 32. And note another point, in these examples, I did not make use of nn.sequential module, because here the layers were built simply one after another, but in most cases you will be using nn.sequential, and in that case your conv 2D and linear cannot be put in the same sequential section. Let's see an example to understand what I mean. So I am just going to my own GitHub, where a few days back I implemented a Linet 5 architecture, which is exactly the same like this PyTorch tutorial. So this is actually Linet 5, and I implemented it a few days back from scratch. So this is the code. It is the same structure. Input is 32 by 32, and then it goes through convolution, then fully connected layer. So let's see the architecture where I have it. Yes, so this is the code where the architecture is built from scratch. So this is what I mean. Say I have self.layer1 that has nn.sequential. It has conf2d, batch norm, relu, and max pool. Then another layer 2, which is again a conf2d, batch norm, relu, and max pool. Now within these nn.sequential, that is the same block of nn.sequential, I could not include my linear layer, and that's because the linear cannot be placed in the same sequential function right after the conv layer. The reason is that the input to linear needs to be reshaped, just like we discussed all this while. So you have to create two sections, one sequential for all your conv layer, and of course their associated pooling and activation layer, and then the output of these is reshaped to a flat tensor, and then this is passed to your linear layer. So this 400 is again calculated just like this, that my last conv layer will return me a 4D tensor, 4-dimensional tensor, that needs to be reshaped into this 2-dimensional tensor to be fed into my linear layer. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one.